So in this example, we're going to look at a problem in three-dimensional equilibrium analysis. So in principle, rigid body equilibrium analysis in three-dimension works the same way. The only difference is that since we're in three dimensions, of course, our equilibrium conditions with respect to no translation, which means that the resultant force has to be zero, along with no rotation about any given point, which means that the sum of all moments about any point has to be zero. They have additional dimensions, and what that's going to allow us to do is to solve for additional unknowns. However, it's just the nature of trying to solve problems by drawing three-body diagrams in two dimensions that can make these problems challenging. So we're not going to look at too many in either the lecture or the homework, but I do want to do a few with you. So what we have here is a plate of known dimension and known mass, along with a pulley of known diameter. And we're told that both are welded to this actual rod that is described by AB since it passes through bearings. Bearings are nothing more than support structures that are going to stop it from moving since it's ideally sitting in there snug. Now, what kind of reaction forces could the bearing exert on the rod? And what that means is what kind of motion can it oppose? Well, if you think about a rod sitting inside a bearing, clearly it's going to be able to oppose motion in both a dimension that is in basically the two cross-sectional dimensions of the bearing, so left and right and up and down. And in our actual problem description here, left and right corresponds to applying reaction forces in the x direction, and up and down corresponds to the y direction. However, generally speaking, you might be able to reasonably take the rod and move it in and out of the bearing. The opposition there is going to come from the friction with respect to the surface of the bearing and the surface of the rod. That is called the axial direction. The reaction that would be applied, stopping motion of the rod going in and out. And what we're told to assume is that the bearing at B doesn't exert any axial thrust. And what that means is that the reaction here is only going to have two unknown components, how much it's having to push in the x direction and how much it's having to push in the y direction. It is not going to be capable of opposing axial thrust, which is just basically motion in the plane perpendicular to the bearing itself. And what we want to do is, under all these assumptions and under the assumption that the actual system is in equilibrium, can we solve for the underlying tension? Now, it seems like a bit of a weird problem. Like, how could you have enough information in order to be able to do that? And we're going to see in a minute how that actually, well, I don't want to spoil too much of this problem for you since it is assigned as homework, but we're going to get it set up for you, and you're going to get to see how that actually works itself out through the homework solution. So let's talk about drawing an actual free body diagram of this assembly. What we want to do is remove the rod from the bearings. We'll have to replace the effect of the bearings on the rod by applying the actual reaction forces. In addition, we want to describe all of the external forces and weights that are acting on the system. So under the assumptions that were stated in the problem, we're only going to account for the weight of this plate. We're going to assume the rod and the pulley itself are frictionless. And in addition, of course, we have the tension of the rope that's slipping over this pulley that we need to account for in our free body diagram. So sorry, I didn't want to actually start again because I wanted to show you sometimes in 3D you got to draw these a few times to get a good drawing, particularly if you kind of rush your free body diagrams like I do. But here we have the pulley, here we have the rod. It's separated from the bearings. However, we've replaced the effect of the bearings by the reaction forces. At A, those reactions can oppose motion both perpendicular, kind of in the plane of the bearings, AX and AY. In addition, the bearing at A can oppose axial thrust, so it's going to have an AZ component. Now, we've talked about beforehand, how do you assume the directions of AX, AY, or AZ, or in general, any reactions in a rigid body equilibrium problem? And the answer is you don't have to assume. You just have some kind of standard convention that you use, and if it turns out that the assumption of your convention is wrong, the signs of those reactions will turn out to be negative. So note that at BX, we've only drawn reactions in the X and the Y direction because we were told to assume that couldn't exert any actual thrust. Now, it's hard to see, but we've kind of set up our geometry such that the face of the pulley is in the XY plane. And since that rope is kind of slipping over the pulley and pulling in that plane, it's going to be purely directed in the X direction. So even though I don't know the magnitude of that force, I can decompose it into rectangular form immediately with the unknown tension T as an X component. Since by our convention it's going in the negative direction, I'll add a negative. It doesn't have any Y and it doesn't have any Z components. Now, how we have the reaction forces, we have kind of the tension described corresponding to the pull on the pulley. How do we actually correspond to describing the weight? Well, we know that the weight is always going to be directed in the negative j direction or the negative y direction. And given the mass, we can compute it by multiplying the mass by the acceleration due to gravity. However, we don't know where the point of application is going to be. It's a little bit complicated because of that tilt beta. So that's where the beta term actually comes into play. So we know that if you look at the original dimensions of the problem. And we haven't talked about this yet in the course. All static texts are kind of weird like this, but you always apply the weight at the center of gravity of the object. And for an object that's highly symmetrical like a plate, the center of gravity is always going to be the point of intersection of the lines of symmetry. It's just a fancy way to say it's going to be in the middle of the plate. So in terms of the actual dimensions along Z, we know that relative to, it depends where you actually set your origin. If you set your origin here, it's going to be 200 millimeters plus 160 millimeters plus 125. Now, how am I getting 125? Well, if that plate is 250 millimeters wide and I know that the center of gravity is at the midpoint, I'm only going to go halfway in the actual z direction for that third step. So the question is, where is kind of the midpoint in terms of the x, which is basically how far out it's swung in that dimension, along with the y, which is how far down it actually is. So if you notice, I've kind of drawn a little bit of a geometry here. I've shown this is a purely vertical line in the y direction. Here we have the surface of the plate, which is inclined from the vertical line by an angle beta. Now, if you notice, I'm describing the geometry, and I'm calling this length here 200 millimeters. Now, why would I do that? Well, if you look at the actual problem description, this plate is 400 millimeters long. However, when I'm talking about its midpoint, I'm only going to take half of that. So I'm only considering a triangle, which corresponds to going down halfway along the plate. And what I'm curious about, sorry, we don't want to see that, is for a hypotenuse that's defined by 200 millimeters, which corresponds to the midway point of the plate. What is the actual x displacement if the plate is inclined at beta degrees, and how far down is it? And we can determine that, again, by trigonometry. We don't know this base. We don't know this base. However, we know for this hypotenuse that this side length, which corresponds to how far out it is in x, is going to be 200 times sine. A good kind of example that you always want to draw out your triangles and not always assume, well, x is cosine and y is sine. In a similar fashion, the y displacement is going to be 200 times cosine of beta. And remember that that's in the negative direction relative to our coordinate system. So I can write an actual coordinate for that point, but what we're going to see in a minute is we're going to kind of use a relative coordinate system to point A. So we're going to need those numbers, but we're not going to go through all the hassle of writing a point. Now, why would I talk about actually using a relative coordinate system about point A? Well, what will happen if we sum all moments about point A, which just describes the tendency of all these forces to induce rotation about point A? Well, if you think about it, all of the reactions at A, they're not going to contribute because their lines of action go directly through that point. So if we sum all moments about point A, the only things that will contribute rotation are the weight, the two components of the reaction at B, along with the tension. So there are four forces there. And when you think about writing a moment equation, sum of all moments about point A being equal to 0, remember that a moment is a vector. So it's going to have an x, a y, a z, or an I hat, a j hat, and a k hat component. And we know that in order for a vector to be 0, all of the components have to be 0. So it might turn out that if I compute the sum of all the moments of these forces about point A, that I can get a set of equations that allows me to solve for easily. I mean, we know we can generally solve for it, right? Because that moment is going to have 3 vector components, an I hat, a j hat, and a k hat. And if those all have to be equal to 0, that's 3 equations, and we can solve for our 3 unknowns, which are t, bx, and by. What I was trying to say by that is you might get a setup that allows you to solve for t easily. So let's talk about actually computing these moments of these 1, 2, 3, 4 forces about point A. So what are we going to need? Well, we're going to need a position vector from point A to the point of application of the weight. That's why we had to do all that work to find the actual center of gravity of this plate. We're also going to need a position vector from point A to point B. That's going to be easy. That's just going to be purely in the negative z direction. And we're going to need a position vector from point A to the point at which the tension acts on that pulley. That's going to be really easy too, because we're just going to have to go in the negative z direction, the entire length of the rod, and we're going to have to go in the y direction corresponding to the radius of the pulley. So that's why we needed that diameter of the pulley. So that's all that I've done here. Is I've noted that only 3 forces will contribute rotation about point A, namely the weight, the reaction of B, which has an x and y component, but I can just represent it as a vector along with that tension. So all that I need are position vectors from A to the center of gravity of the plate, from A to the actual point where the bearing touches the rod at B, and from A to D, which is in our original geometry, defined as the point at the top of the pulley here. So we said that the position vectors from A to D and A to B are going to be quite easy, and that is in fact the case here. If you notice to go from A to B, sorry, I should say A to B here, we're going to go purely in the k-hat direction. And if you, y is at negative, well, if you look at the actual setup of the geometry, from A to B is going in the negative z direction. So you just want to sum these three things together, 160, 250, and 160, and then make it negative. And that is exactly what I have done here, negative all those sums. If you talk about A to point D, that is the actual point at the top of the pulley here. As we mentioned, it's going to have a minus z component, and it's going to have a plus y component. The y component is just 300 divided by 2, and the z component is just negative, all of those dimensions added together again. So that turns out to be 0, 150 minus 770. It makes sense because to go from A to there, you got to go up in y, and you got to go negative in z. The AB is purely negative in z. And remember that in order to go from A to G, in addition to having to go in the negative z direction, you got to go a little bit right and you got to go a little bit down. Well, how much right do you have to go in the x dimension? That's just going to be this 200 sine beta. That's like saying to go from here to here, you have to go a little bit to the right and a little bit down. The y component is just going to be minus 200 cos beta. So that's why you had to do all that work to find the x and y location of the center of gravity. So once you do that, you'll get these three position vectors. You can express the three forces that are exerting rotation about point A. The weight is purely known. It's just in the negative j direction, and you know its mass, so you can just multiply by the acceleration due to gravity. The tension, the magnitude is unknown, but you know it's directed in the minus I hat direction. And then B, the reaction, it can exert an axial force, so it only has an x and a y component, both of which are unknown. So you can take and compute the cross product of each of those three position vectors times forces that you need to do. Some of those are going to involve unknown quantities, and I didn't want to spoil the fun for you, but when you do that, you should be able to get three actual equations here for the actual, if you think about it, this cross product is going to have an I hat, j hat, and k hat component. Same thing for this, same thing for this. Combine all the I hats together, combine all the j hats together, combine all the k hats together. Remember that each of those has to be 0. So you'll have three independent equations, which will allow you to solve for the three independent unknowns. However, the only one that you need is t for your actual homework problem.